Alright, start writing.
Wait, there's orange in your shoes.
You're right, there's a little bit orange here.
Yeah, you just had to wear orange. Is your favorite color orange?
Yeah.
It is?
No. Alright. So, I guess I should define this first, right? So, reaction rate is the amount of reactant used up per unit time. So everybody knows in a chemical reaction you have reactants. Those are the things you start out with. They're like the ingredients for the reaction. And then you have products. That's the stuff that's made in the reaction. And so what this really means is the speed at which reactants are used up. It just means how fast the reaction is going, basically. Right? So that's really what the definition is. How fast these things react. All right, so a couple of things I'm going to go over. Basically what I'm going to talk about today is things that affect reaction rate, things that speed up chemical reactions and slow them down. So before I can talk about that, I got to give you two things, two definitions here. So one is collision theory. And these are the two things basically that tell you if a reaction is going to happen and how fast it's going to happen. So collision theory says things react when particles bang into each other. When I say particles, I mean atoms, ions, molecules, any of those, right? So if we think about, like yesterday I talked about combination reactions. And I said a combination reaction is when two things come together and they stick together, right? Mm-hmm. And that's kind of like when two people meet and they get married and live miserably, whatever. So if you want to think of that, right, then collisions are like that. It's like people bumping into each other. People have to meet at some point to stick together, right? If they never see each other, they're never going to be together. So same thing, particles have to actually come in contact at some point for them to stick together. So for a reaction to happen, particles actually have to bang into each other. The other part of this is activation energy. Activation. And so when particles bang into each other, they have to collide with enough really enough speed, because we're talking about kinetic energy here, so it translates mostly to speed. So they have to be going fast enough so when they bang into each other, the reaction happens. So if they don't have enough energy, the reaction won't happen. And so the minimum you need is this here, activation energy. It's the minimum energy needed for particles to react. So it's pretty straightforward. If they collide and they have at least that much energy, they're going to react, and the reaction is going to happen. If they don't, they're just going to bounce off each other and nothing's going to happen. That's it. Okay, so now I'm going to talk about things that speed up reactions. So we'll call this factors affecting reaction rates. And you might think that this is a minor thing, but it's actually a big deal in chemistry because some chemical reactions that you want to happen might take, hours or a day or a million years to happen, whereas if you put in something to speed up that reaction, it might happen in a few seconds or a few minutes. In your stomach, for example, if you don't have the right enzymes to digest things, right? It'll just sit in your stomach until your stomach decides to get rid of it after a couple of days, and then you have diarrhea. Whereas if you have the right enzyme, you digest it and get the nutrients you need out of that food. So, like milk, you wouldn't digest it. It would just sit there for years. And, well, it wouldn't sit there for years, but if you tried to digest it, it would stay there. So, all right. So anyway, factors affecting reaction rates, there's 4.5 of them. So let's do number 1. Anybody want to take a guess? What's the one thing that seems to affect everything in chemistry?
Love.
Water?
No.
Air.
No?
No.
Temperature.
Temperature.
All right. You guys were on a different planet from what I was looking for, so
Chemistry.
just so if you raise temperature, you're going to have faster reaction, lower temperature, slower reaction. So higher temperatures speed up reactions. And I'm going to explain why. And so for each of these factors that I give you, I'm going to explain them in terms of these two things, collisions and activation energy. And temperature affects both of them. So how does it do it? Well, when you raise the temperature of something, what are you doing? You're speeding up the particles. You're making the atoms or the molecules move faster. And if you do that, that means number 1, there's going to be more collisions. And number 2, the particles that collide are going to have more energy, so more of them are going to have enough energy to react. They're going to be above the activation energy. So higher temperature means more collisions. So let's write that. More collisions. Collisions. And more particles are above the activation energy. Because not every particle has the same amount of energy. They're all just kind of randomly moving around. When you heat it up, the overall average goes up. You know, a lot of the particles get sped up. So the more particles have
Pardon this additional interruption
enough energy.
as an update, and something we started this year. 3 teachers started it, and we certainly appreciate it. Congratulations to everyone who qualified for the Renaissance program. Homework coupons, physical education coupons, and snacks can be redeemed today in the library all day. Thank you.
Can I race up to here? Okay, sounds good. I'm so glad there was an interruption.
Did you say to me? Yeah, that's don't you dare.
Not now.
Number 2. Particle, no, concentration. I don't know. I was already upset about the announcement. It's not like I put effort into making my class quiet so my students can concentrate or anything. Anyway, concentration means, you know, how tightly packed things are, how close together they are. I mean, in solution, we're talking about how much stuff per volume, right? But what that translates into is how closely packed the particles are. If you have a small volume with a lot of solute, then it's very concentrated. If you have a big volume of liquid with very little solute, it's spread out. And so you can kind of think of concentration with people, right? Imagine if I had like the gym with 1,000 people in it. That's highly concentrated. There's like 1 person per square foot. You're all bumping into each other. Versus if I had the gym with like 2 people in it, that'd be a low concentration of people in the gym. And so if you want to think about this in terms of collisions, where are you more likely to bump into other people? Well, if I had 1,000 people in the gym, you're constantly bumping into people. You're probably going to make some new friends, right? But if I had 2 people in the gym, they could be sitting on opposite sides of the gym and never meet each other. So higher concentration means more collisions. So there we go. Higher concentration that one? Did I spell it wrong?
No, it's good.
Oh, okay, good.
She spelled it wrong.
Higher concentration speeds up reactions. Reactions because there are more collisions. And keep in mind, there are times when we want slower reactions, right? Like if you have a reaction that gives off a lot of energy, like when I did the sodium and the water, well, if I had a higher concentration, If I took a big chunk of sodium and threw it in the water, well, we would have got a bigger explosion. That would have hurt somebody, right? So there's times when you want to slow it down so the amount of energy given off isn't so great, so you don't have fire and heat and explosions and kill people. So you can use it either way, faster or slower reactions. All right, 3. 3 is particle size.
Bless
you. Can you see the camera from where you're sitting?
Yeah.
Okay. Can you see my hands right here where they're at? Can you see them on the camera?
Yeah, barely.
Okay, good. All right. So,
You probably just remember this word
let's calm down. Can you see these?
Just the
Yeah.
tops of them.
Tops of them? All right, go fix it. Thank you. All right, so I want you to think of these textbooks as if this is one big block of solutes, and I drop it into some sort of water. No, wait. Good? Thank you. You can just leave it like that. All right, so imagine this is some chunk of salt or something. It's a big chunk of salt, and I drop it into some solution. It's going to react with something else. The reactions happen at the surface because that's where the liquid touches it. So it happens here, happens on top, on the front, and on the back. Not on the inside, obviously. So that's the only places it can react, which means the reaction is not going to happen too fast. But if I broke them apart, right? Imagine I took my solute and I smashed it up into little pieces. Well, all of a sudden, there's a bunch more surfaces. There's this surface touching the solution and this one, and reactions are happening on all these surfaces too. So by breaking it up into smaller particles, I have a faster reaction because there's more surface area. It's the same reason if you're eating a lollipop and you chew it up, well, more sides of the lollipop are touching your saliva, it dissolves faster. Whereas if you leave it a whole piece, it can take an hour to dissolve. So same thing. All right, so smaller particle size equals faster reaction. And there is times when you want the opposite of this, right? Like if you're taking a multivitamin and you don't want it to get used up so fast, you want it to last for 24 hours and slowly put the vitamins into your bloodstream so you don't pee them all out in the first hour, well then you don't chew the vitamin. You want it to go in your stomach as a whole, and then you slowly eat away at it over time. So that's why sometimes you're not supposed to chew those things.
Swallow them?
Vitamins, yeah, the ones you have to swallow. Because when you take a vitamin, right, the B and C vitamins are water soluble. So if they go into your system, within an hour or two, they're gone. You use what you need, and the rest just get peed out. So it's good if you have one that lasts for a long time, and it slowly puts the vitamins in your bloodstream, so you have them all day.
Right, so that's why you shouldn't, like, if you take a pill, instead of, like, say if you're scared to swallow it, you can't break it up and put it in water and drink it.
Yeah, because it would get absorbed too fast. Sometimes that's the case. There's other reasons too.
Why?
Sometimes
What
it just
happens if it gets absorbed too fast? What is the stick?
can have a really strong effect on you.
Like what?
Or it could just get used up, and medicines go to you quickly too. But I mean, sometimes the medicines have side effects. So if you get taken in too fast, it could hurt you. All right, let's go on to number 4. 4 is catalyst. What are you talking about? What? 4. Oh, okay. Yes, you said 4. Good job. What am I doing? Catalyst? So catalyst, this is a stupid definition, but I'm going to write it anyway. So it's something that you add to speed up a reaction. So this is like, you got your reactants, you put them in, and then there's this third thing you mix in there that's going to make it react faster. Usually 2 or 3 choices. Metals sometimes will speed up a reaction because they give the reaction a place to happen. Acids sometimes speed up reactions, and enzymes. And I'll talk about some of those in a second. Let me erase this here. Something to know, they has an E in it. They are not reactants or products. And what I mean by this is they don't get used up in the reaction. Right? You put an enzyme or you put any kind of catalyst in there, and it can work over and over and over. So if we go back to thinking about a chemical reaction as people meeting and getting married and falling in love and all that stuff, right? So think of the enzyme as like the matchmaker. They bring the two atoms together and make them react, and then the new product goes off by itself, and the catalyst can be used again and bring two more together and send them off and bring two more together. So it can work over and over and over. It doesn't get used up. All right, I told you there were 4.5. So here comes the half. These are enzymes. So enzymes are not a separate category. Enzymes are catalysts, but they're an important important group of catalysts, so I wanted to talk about them a little bit. Enzymes are biological catalysts. And I just said that because I want to sound smart. What does that really mean? It means that they're made from living things. You make them in your stomach or in your cells and stuff, right? So what are they? They're basically catalysts that are made of protein. So we'll just put that in, made of protein. Right. Anytime your body wants to make something, right, like the structure of your body, what's it made out of? It's made out of protein, right? That's what that's what holds us together, keeps us in one piece. So anything that you make in a cell is made of protein. And so these catalysts, they just, like I said, they bring things together and make reactions happen, or they break things apart and make the reactions happen. And if you didn't have these, the reactions would happen so slow that you wouldn't digest your food and probably would die of starvation because you couldn't break down the food that you were eating. So you need enzymes for that reason. There's one other one I should throw in here. Let's make that 4 3/4, just for fun. And I'm going a little crazy with this. Inhibitors are another group of catalysts that you don't hear about much, and these are catalysts that slow down reactions. I know, it's a weird list. Don't get mad. Catalysts that slow down reactions. I guess if you were looking forward to the number 5, you could have set something up. So we don't use those very often, but there are ones that you can use if you want a reaction not to happen too fast. And that could be because you don't want things to get too hot, right? So something could give off a lot of heat, and if it gets hot, that might destroy what you're trying to make or something like that. Questions? You good?